Welcome to Physics 142 Online. We're now going to pivot and make a change of topic in the course from our study of waves, and in particular light, to electric and eventually magnetic fields, and exactly what they cause, what kind of effects that they produce on matter. And so today this is a very brief introduction, and I hope that some of this will be familiar to you from previous courses. Let's just look at Coulomb's law. Coulomb's law is a summary of experimental evidence that gives us the forces that two point charges exert on one another. And so by just using a very simple force equation here, that the force is equal to a proportionality constant times the charges Q1 and Q2 divided by the distance between those charges squared. This is the familiar Coulomb force law. It only gives us the magnitude. We'll have to determine the direction of that force using the sign of the charges. But let me just say at the outset that the unit of charge in the International Unit System is the coulomb. And so if we use charges in coulombs and the distance r in meters, the proportionality constant that is in Newton meter squared per coulomb squared, then the force will be in newtons. So the direction is determined from the sign of the charges. Of course, opposite charges repel, and like charges repel, opposite charges attract. So let me be clear about that. Like charges repel, opposite charges attract. Positive and negative charges attract one another. Positive and positive charges repel one another. The Coulomb constant, which is the K in this force equation, is usually written by physicists in terms of a different constant, which we think is just slightly more fundamental, and 1 over 4 pi epsilon 0 replaces that K, where the epsilon 0 is used, is described by the term the permittivity of free space. And so if you just take 1 over 4 pi epsilon, or 1 over 4 pi times K, you'll calculate an epsilon 0 value of 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. So it has the reciprocal units of K. Some homework problems, it's easier to use the Coulomb constant. In others, it might be easier to use the permittivity of free space. So in a specific example here, you can see that we can determine the directions of the forces on various charges using unit vectors and using unit vector notation, just like we did in our study of mechanics. So in the diagram here, you see charge 1 on the left, charge 2 on the right. Charge 1 is positive Q, charge 2 is negative Q, and the two forces, if the charges are separated by a distance d, can be written like this. F1 represents the force that charge 1 exerts on charge 2. So F sub 1 means the force produced by charge 1. And so, right away we know that charge 2 is going to be attracted, so it will feel a force to the left. So that's K times the product of the charges, their magnitudes, which is Q times Q, so KQ squared, over the distance d squared, and if the r direction in our coordinate system is to the right, then the r hat unit vector goes to the right. But we know this force, the force that's produced on charge 2 by charge 1, is to the left. So this force has magnitude KQ squared over d squared, but it's got direction minus r squared. So let me again emphasize that I'm not plugging in a minus sign in for the charge in this equation up here. What I'm doing is I'm saying let's take the product of the magnitudes of those charges and then determine the direction of the force by remembering that opposite charges attract and like charges repel. Similarly, the force that charge 2 exerts on charge 1 is the force labeled F2 on the diagram, and that will have magnitude KQ squared over d squared, and the direction, of course, is to the right because the positive charge is attracted by the negative charge. So it's in the positive r hat direction. And depending on our coordinate system, this r hat could be I or j or k, just depending on the unit system, on the coordinate system. So that's basically Coulomb's law, and we can now look at a system of point charges, because if we know how to find the force that one point charge exerts on another one, we can then use vector addition to find the net force that a whole collection of point charges exerts on another charge. When we want to do this, you'll see in the diagram we've got a red charge, and we're going to try to write down what the net force is on that red charge due to Q1, Q2, and Q3, the blue charges. And so we first define a coordinate system. We would put in an x and a y and perhaps a z-axis. Then we would want to write each force, F1, F2, and F3, in vector form using components, vector components, and the unit vectors I, j, and k, and then we would simply add the force vectors vectorially, as vectors should be added. So look at the diagram again. The force on the red charge due to charge 1 is F1. All right, I've drawn it like this, assuming that these charges all have the same sign, so that would be a repulsive force. F2, the same way. It's the force that charge 2 exerts on the red charge. And then F3 is the force that charge 3 exerts on the red charge. So this does not show a coordinate system, but let's do an example that does show the coordinate system and has 3 charges. One charge B sitting at the origin, charge A on the negative x-axis, and charge C on the positive x-axis. And the question, if these 3 charges are sitting on the x-axis, and if the 2 distances involved are d, we want to find the net force acting on the charge at the origin, charge at B, due to the charges A and C. So here's the problem again. We've got these 3 charges lying on the x-axis, and we assume that they're fixed in place. So given the 2 distances that separate AB and then that separate B and C, given the charges for each of the charges, we want to find the net force acting on the charge at point B, which is at the origin in this coordinate system. So how do we do it? Well, we first want to write down expressions for FA and FC, once again using the familiar unit vector notation. The coordinate system has already been written down for us, and so we can write down F sub A, right? And again, we write down the magnitude first, and we put in the direction using the signs of the charges. So the magnitude will be K times the product of the magnitudes of the charges, which is 3Q, right, times 2Q. I'm not putting the minus sign in here. I'm just writing down the magnitudes, divided by the distance squared, d squared. So that's the magnitude of that force, but we need the direction. And the direction is indicated already in the diagram because we know charge B is negative, so it will feel a force from a positive charge pulling it to the left. So FA is in the negative x hat direction. So I'm going to put over here negative x hat because of what I know about positive and negative charges. And let's do the same thing for F sub C. F sub C, first I'm going to write down the magnitude. I've got 4Q and 2Q. So the Coulomb constant K times 4Q times 2Q, again over d squared. The distance is the same as it was for F sub A. And then let me look at the direction for F sub C. Well, here clearly, again, the negative charge at the origin experiences an attractive force from the positive charge, so F sub C is in the positive x hat direction. So I'll just write x hat like that. And what I want, of course, F net is simply the vector sum of A and C, F sub A plus F sub C. This problem makes the calculation simple because both forces act along the x direction, either in the positive or negative direction. If you have a more complicated problem, and there are a couple of them on the homework, you will have forces that have components in both x and y directions. So then you'll have to, when you write down your vector equation, you'll have to then break down those vectors into x and y components using some trigonometry, and you'll have to add together their components. But in this case, it's actually very easy. So let's just finish it off. We've got then that F, the net force on the charge at point B, is the sum of FA and FC. So FA, if I simplify that a little bit, right, I've got 6K Q squared over D squared in the negative x hat direction, right? So that's the FA. F sub C is 8K Q squared over D squared in the positive x hat direction, like that. And those x hats I can factor out of the expression, and I basically have now 8k q squared, right, over d squared, minus 6k q squared over d squared, and just put the x hat outside like that. And I've taken into account the signs by the way that I wrote down the two terms. So this should be easily seen to be exactly the same as what I had before. And now I simplify this, and I'm going to get the answer, which is about all I can do with this, 2k q squared over d squared in the x hat direction. And that's my result. If these 3q and 4q charges are equally distant from the charge at point B, it stands to reason that the larger of the two charges is going to win out, is going to have a larger force than the other one. So F sub C, it's pretty clear from the picture, is larger in magnitude than F sub A, so it makes sense that the final net force is in the positive x direction. So once again, we're just using the simple principles excuse me, of vector addition, and in this case all we had were x components to add. Some of the homework problems will require you to do vector addition using x and y components, but the basic principle is just the same as this. So this should be helpful as we begin to work homework problems involving Coulomb's law.